Hello everybody, this is Carol speaking. Welcome to our PolyWorks webinar. Today we are talking about how to inspect parts without CAD models, all the while using a probing device. Let's welcome Roberto Barreto as he is our presenter today. Roberto is a member of the technical support group. Let me remind you that if you have any questions during the webinar, please use the questions panel. I will be monitoring the questions throughout the webinar. If we don't have time to answer all of the questions, we will get back to you by email. And yes, we are recording this webinar, so it will be available for later viewing. Roberto, it's all yours.
Thank you, Carol. The reasons for performing an inspection without using a CAD model can vary significantly. In some cases, the CAD model might not have been provided by the client. In others, it simply does not exist. And in some cases, the measurements required are so simple that it is simply not needed. This webinar will present how to use PolyWorks Inspector to inspect parts without using CAD models with a probing device. In this first example, our goal is to measure the GD&T controls shown in this 2D print. This includes a flatness callout as well as a concentricity callout relative to data main. As in some previous webinars, I will use a transparent model to represent the part that we will be probing, for display purposes only. Before we start measuring, let me bring up the Features toolbar, which facilitates the access to different types of features, which is particularly helpful for probing-only workflows. Let's begin our measurements by probing our data on plane B. And I will make sure to use a continuous probing, since that will allow me to get many points to get a good flatness reading, as well as a uniform distribution of such points. One thing you will notice is that as soon as I have more than 3 points measured, a form error will be displayed on the top right corner, right here, and that value is actually updated every time I take additional points. This will allow you to troubleshoot your measurements even while you're measuring a very specific part, in case, for example, that value exceeds a value that you're normally used to seeing for this type of part. And if for some reason a point actually makes that value go beyond a previously specified threshold, you will see a warning message like the one you see on the screen now, allowing you to either undo the last point, reprobe the whole object if you're not really sure at what point the mistake might have been made, or continue probing the object if you think the points are still valid, or if you're planning to actually remove them later using additional tools. In my case, I will undo the last probe point and even remove a couple more points, since it's not uncommon for operators to lift the probe from the part before actually stopping the acquisition, which might cost more than 1 or 2 points to actually be away from the part. I will complete the measurement of my data on plane B now, and I can use geometry controls to add the flatness control that was required. To continue our measurement, I will now go ahead and measure my datum cylinder A, and I will make sure to go back to single probing since I don't need to do a form control on that particular cylinder. In any case, for a cylinder with every time you get more than 6 points, you will still see that form error being shown just to guide you during the probe. And an additional cylinder that I'll need to measure is the actual cylinder that we need to measure for the measurement of the concentricity column. For that one, I will make sure to really go all the way around, as with the other one. And once we have our 2 cylinders measured, we can go ahead to geometry controls again and set up the appropriate concentricity column relative to that data main, which will give us the result. Now what's required? And for dimensional controls, like the diameter of the cylinder that I just probed, nominal values can be entered directly into the geometry controls pane. This will automatically calculate the deviation, and by assigning the adequate tolerance, you're going to also get a pass-fail status for that particular feature. If I go to my datum A, I can do the same thing. Set the adequate tolerance. And at this point, my measurements for this particular project are complete. If I hide the display, the model that we're using for display purposes, this is what your actual probing result would look like. And I would like now to report those results. But before I do so, I would like to actually create a coordinate system, since all of my, the location of my points now is just randomly positioned based on the position of the device. So I would like to create a local coordinate system using my datum A and B. And I will make sure that my Z-axis is actually pointing towards the inside of that particular datum A. By doing so, I now have access to normal views or even a nice isometric for the report on my results. I can now position that the way I want and create a control view for the values we see on the screen, which will give me a report for all of the required measurements. Now that we have obtained the desired results without using a CAD model in this simple scenario, let's take it one step further to see how we can set up a more complex project for a multi-piece inspection. In this project, I've already probed datums A, B, and C, and I've created an intersection line between datums A and B, and an intersection point in between my three planes. They're going to be helpful for alignment later on the project. In addition to that, I've measured my left and right circle, which are required to obtain the measurements shown in this 2D print, which contains some position controls, as well as some basic dimensions to position the holes in space. Those of you familiar with the typical CAD inspection workflow know that it's a good idea to align your device to the CAD model as soon as possible. This is still the case when no CAD model is available, since being aligned to your nominals allows you to use guided probing, see if you're probing the right object at the right time, and when no CAD model exists, this is also required to be able to create distances and nominal primitives using the right coordinate axis. In this case, since we want to build a multi-piece template, we are going to use our datum plane A, line, the intersection line, and the intersection point to align our measurements to the world coordinate system, instead of creating a secondary coordinate system like we did in our previous example. Proceeding in this way will give us better control on the degrees of freedom blocked by each one of the features. It will also allow us to define nominal primitives, which is a requirement for position callouts, and we can do so numerically. And finally, if a CAD model ever becomes available for this project, we can import it and update our project using it. For the alignment, I will have my datum A plane match the XY plane of my coordinate system. I will have my intersection line match the plus X axis. And finally, I will have my intersection point match the origin of my coordinate system. And once this is done, I will have a nice normal point of view that I can use to review my results. In addition to that, I can now go ahead and define the nominal primitive for my circles numerically by using the values shown in this print. For example, a 60 and 62 coordinate for that left circle, as well as a nominal radius that matches the print. If I do the same thing for the second one, in this case using a 20 and 55 as the nominal coordinates, you will see that automatically all of the values for the nominal, deviation, and test are computed in these values, are being computed with the new values, and the true position control is also computed at the same time. Another advantage is that because we are now aligned to that coordinate system, we can now create distance features along specific axes, like a horizontal distance, a vertical distance, or even both at the same time. And because we have defined nominal primitives for both of our circles, you will see in geometry controls that not only the measure was calculated, but also a nominal distance was calculated using those primitives. At this point, I would like to create a report for those results for my multi-piece inspection, and I would like to show something similar to the print, so basically my three datums, A, B, and C, as well as my circles and my distance results. But keep in mind that all throughout the webinar, I've been using a model to help you understand where those measurements are located. But your real project would actually look like this. So if you create that top view, that top control view, this is what your report will actually look like, which is not going to be easy to understand for people that are not familiar with the shape of the part. So one thing you can do is you can simply replace that image by copying and pasting your drawing directly into the formatted report. What this will give you is a drawing that people are used to understanding because the client might have provided or because it's what they're used to seeing, combined with the results obtained in PolyWorks by probing the part. At this point, one final thing I can do is try to guide operators during the probing of the features. Remember, there's no CAD to guide them to or to tell them which feature they're supposed to probe at any specific time. And that's particularly needed when you're probing planes, the initial alignment planes. So one thing I can do is I can go to the properties and add guiding instructions and a guiding image, which in this case will be the print, so that when they measure a new piece using this newly created project, they will now, instead of seeing just a blank screen, see a message telling them to refer to the print to see where datum plane is, and they'll see it on the screen directly without having to look for an actual sheet of paper. And the same thing will apply for datums A, B, C, and so on for the remaining of the project. All of this summarizes how you can inspect parts by probing when no CAD model is available.
Thank you, Roberto. So let's go to the questions. The first one refers back to the very beginning of your webinar. You talked about a threshold for form error when you were probing. Is that threshold adjustable? Can we adjust it?
Yes. So when I was probing datum B, I was showing you that there was a warning message when you exceeded a threshold, and that's actually a value you can control from the PolyWorks inspector options under objects, features, probe acceptance. So here you see the normal tolerance or the default tolerance is 1 millimeter, but I can change that to 5 or anything else. And you also have other controls like size and standard depth that you could add based on your application.
Thank you. Okay, second question. You also mentioned that we could delete points after probing. How can you do that?
That's another very good question. So to delete points after probing, there's actually more than one way to do it. I think one of the best ways, specific, especially if you're looking like for a specific point to delete, is that you can go to the properties, to the edit measure points window for a very specific feature. And this will show you a list of points that you can actually sort in order to find an outlier or a point where you might have lifted the probe before you confirm. So you can remove it from there and that will update your results or your fit for the probe. Alternatively, you could also use our select elements tool to select one specific point or maybe a couple, and then hit delete on your keyboard to remove those. And if you need like any help trying to figure out who those points are, you could probably even use our display option that allows you to see both the deviations of that plane as well as the min-max deviation for it. So it could look something like this. You could really see who the bad points are and try to remove them from there.
Okay, and one very last question we'll squeeze in right in. Can you show again how to put the print, the engineering drawing on the feature when you're probing?
Sure. So I have it. So I'm going to do it in this case. So I did it for the other project where we had the print on the as part of the report. We could see it here. So I'm going to do it for the other project, which I didn't do it. I just left the cylinders there. So again, I can just delete the snapshot that was provided. And then from the, you can use actually, if you have a snipping tool to get part of the drawing, you could do that. Or you can just simply copy any image. In this case, I'm copying the whole print. And then on my report editor, I can go ahead and paste that into our report in any location. And like any other image, you can resize it if you want to have it smaller here and have it in your report.
And what about on the features?
On the features, yes, that's a good. So on the features themselves, so in this particular project, if you wanted to show that drawing on the datum plane B, you go to the properties. Then under measurement, you have the guiding instructions right there, and you can add an image there that you can import. In this case, it will be the first drawing, and when you do that, anytime you probe that feature, like if I were trying to probe it again, then you'll see it right there on the bottom left corner.
Thank you, Roberto, and this is really all the time that we have for the questions. This webinar has been recorded. It will be available on the Innovametrics software website. Navigate to the About Us section. So a little heads up, we're moving things around. So the About Us section. The webinar will also be available on the Innovametrics software channel on YouTube. Our next webinar is scheduled for December 12th, and we will be talking about how to simplify adding 3D inspection results to corporate Excel reports. Thank you for joining us this morning, and we'll see you next time. Bye-bye, everybody.